much. So, we've heard a lot about demand side reduction, and that's also very much true in the cement field. But I'm not going to talk about that today because, you know, we also got to find solutions to the big need for cement. So the situation today is that concrete and mortar are irreplaceable. People think they're high energy materials, but this is completely incorrect. The only reason they have this very big impact is because of the tremendous amounts we use. We use more than 30 billion tons of materials based on cement every year. So a lot of people may talk about timber as a very nice option. That's fine, but to be realistic, we only have about enough timber to replace about 8% of building materials today, and it's been estimated if we wanted to replace just 1/4 of cementitious materials with timber, we'd have to plant new forests 1.5 times the size of India. So while these may be nice materials, we just really have to realize that they're not going to take us very far on the scale, at least to 2050. And demand is going to go up mainly in the global south. So China, I think, has now peaked. It's going down, but India is coming up. And then other countries, notably in Africa, the demand for cement in Africa by 2050 is forecast to increase by about tenfold. So where would we go with these emissions? Well, we are limited by what we have available. So unfortunately, most of the emissions which are coming from cement are due to this breakdown of limestone, calcium carbonate, which breaks down to calcium oxide and CO2. So people say, well, can't we produce something different? But the long and short of it is that Portland cement is actually an inevitable consequence of the chemistry and geology of the earth. And there's no material which can substitute it in the quantities we need. But that doesn't mean we can't do anything, because we can very much do anything. We can substitute a large proportion of these materials by what we call supplementary cementitious materials. So this idea has been around a long time, but today the materials we're using as replacements are what is called slag and what is called fly ash. So fly ash comes from burning coal, which of course is the first thing we've got to do to prevent climate change. And slag comes from the production of iron, where also it's really imperative to find better low-carbon solutions to production of iron. And when we really review what's available on Earth, we see, well, we've got an awful lot of limestone, and we can't use that as an additive when it doesn't break down, doesn't give off CO2. But we can only use a certain proportion of that without losing the performance. And really what we realized was the only material that was available in the kind of amounts we needed was clays that could be calcined. So this is what led us to the idea of what we call LC3, that to realize that this strategy of substitution was the best strategy because it can be done by everybody, it can be scaled, it can be developed very, very fast, but the only material available in the quantities we need to expand this technology is calcined clay. And then we realized that if we combined calcined clay together with limestone, we actually got a synergetic reaction which allowed us to go to even higher levels of substitution. So this is the idea of LC3. On the left here we have the composition of a classic cement and the associated CO2 emissions. We have most of the emissions coming from what's called the clinker. And in LC3, we replace at least half, and we can replace even more than half, but at least half of that material by the calcined clay, which has much, much lower CO2 emissions, about 1/10 of that of clinker, with limestone with no CO2, and with gypsum. And the nice thing is that we don't lose anything in terms of performance. So even by a few days, we have higher strength than in the reference Portland cement material. So here we have used 50% less clinker, 40% less, that equates to 40% less CO2, and we can have similar performance in some respects, notably with resistance to chlorides and alkali silica reaction, which are two problems of durability. Then we have much better performance. So our key question at the beginning of this work we were doing was really to identify what kinds of clays. And this is very important because we found we only need about 40% of this mineral we call kaolin. We don't need very pure clays. We just need, really common or garden clays you can find really everywhere. And so this does not compete with other applications. This is another misunderstanding a lot of people have. And in fact, even better, we can often use wastes of other mining operation for this material. And the kind of materials we want are super abundant worldwide. Everywhere you can see on either of these maps this kind of orangey yellow color, you will have suitable clays for producing this cement. And very nicely, these clays are most abundant in just those areas of the world, like Africa, where the demand for cement will increase most in the coming decades. So with our partners in India, notably Tara and the Indian Institutes of Technology, we've really been able to take this technology to full scale. This is the demonstration house they built near Jhansi. And in this one single house, we could demonstrate that you're saving around 14 tons of CO2 compared to existing solutions. And based on this sort of pilot work we did very much in India, we now have full-scale plants. This is the plant in the Ivory Coast. There's probably only about 4 or 5 around the world today, but we know of at least 30 or more projects which are coming online in the next 1 to 2 years. And this is really seen now as by the big companies as the most viable option for reducing CO2 fast and at large scale. What's even more interesting is it's actually cheaper. So rather than having to pay a premium, we can actually reduce the cost of production compared to the reference Portland cement. And that's extremely important because, while we all want to reduce CO2, we have to be realistic that what drives industry is cost reduction. And if we can offer them this cost reduction, we have a lot more chance that they will take this up. And so coming back to the potential, well, this graph here shows the current levels of substitutes today, and this has stagnated at around 20% for the last decade or so. Now, when we remove the limitation that I told you about at the beginning from the availability of slag and fly ash, then we can certainly go to a much higher level of substitution, such as 40%, which would be equivalent to saving 400 million tons of CO2 per year. And that's like about 1% of the emissions worldwide today with just one single technology. But I think, in fact, on a horizon of 2050, we could imagine to go much further than that. We could reduce even by double or more which would save around 800 million tons of CO2 a year. So this slide just summarizes why this is a very interesting technology, because it can save CO2, because it limits the use of scarce resources. We can use waste sources. We can have the same performance as the material today, and it can be used in exactly the same way. You can substitute one-to-one. It's a technology you can really roll out at full scale. So this is how we're tackling reduction of CO2 in the cement and concrete business, but this has to come together with the kind of measures we've heard about in previous presentations of reducing demand. And we can reduce demand without really any compromise, because It's been well demonstrated that most buildings today are over-designed and typically contain 30% more concrete than they need. So we haven't even got to change any codes, we've just got to make sure that people stick to the limitations that are already well established. So thank you for your attention. The QR code here gives you a more detailed brochure on this material, and if anybody's got any questions, feel free to contact us later. Thank you.